for sure.
Yeah. Of course, I did want to talk about Kepler's laws.
Oh,
so Kepler,
100%.
Johannes Kepler,
Ooh.
right? He is a famous astronomer. I don't know if he was a physicist or anything else like that, but he's most famous for his astronomy and his. This was back in the 1600s, and he used to look at planets and try to explain everything that was going on. Back in the day, my favorite expression, right? Back in the day, everyone thought that orbits were circular because, you know, the space and God is perfect, so everything must move in perfect circles. And that idea delayed a lot of advancements in the field, because you have to actually let go of that idea to make accurate calculations. And this is actually one of Kepler's laws. His first law, actually. And it's the law of ellipsis. So this law is pretty simple. It just says that every body in space goes along an elliptical orbit. And so turns out that a circle is a special case of an ellipse, but it's very rare to find a perfect circle orbit. Turns out the Earth is, of course, on an elliptical orbit, but it is very close to a circular orbit, but it's not exactly, right? That's why you can kind of approximate the distance from the Earth to the sun, but sometimes during the year we're actually closer to the sun, sometimes we're actually further from the sun. It also turns out that that doesn't have much of an effect on the heat being received.
True.
Right?
We spoke about this in the last episode.
Yeah, we did talk about this, but just because you're a little bit closer to the sun on your orbit, turns out that little bit is so little that it doesn't affect the temperature of the Earth at all.
Exactly, because relative to spatial and astronomical distances, that distance is very little. Also talking about, just elliptical orbits, maybe a kind of important term when it comes to that, the semi-major axis, right? So in every elliptical orbit, you have two very important points. You have the periapsis and the apoapsis. Now, depending on what planet or star they're orbiting, they're sometimes called different things. Like if it's around Earth, it's perigee, apogee, right? Yeah, and if it's the sun, it's perihelion, aphelion, stuff like that. But basically, the general term, periapsis, apoapsis. So what do these mean? So in any elliptical orbit, right, there's obviously a center, and there's which is usually, in this case, let's say the sun.
Two.
Oh, they're two. Technically, yes, that is true. But I'm saying in orbits, in orbits, usually there's just one focus in this case, and we have some.
Actually,
distance.
that's not correct either.
Okay.
There are always two foci, but just one of them will have a planet. Or
because it's only orbiting one of them, though.
Yeah, but both of them are still present. Both foci are still there, because every ellipse has two. So you can't just say the other one doesn't exist.
As I was saying it, I wasn't sure about that. Okay. So I guess. Anyways, the point I'm trying to make is
the thing is that there's always two, but the thing that the object is orbiting around is at one of the foci.
Okay.
That's it.
Okay, so there are always two. It's at one of them. Okay. Anyways, the point I'm trying to make is the apoapsis is the largest distance that, let's say we're talking about the Earth. So the apoapsis is the largest distance that the Earth is from the sun. So the farthest it's away. And the periapsis is the closest it's to the sun. So every single orbit will have a periapsis and an apoapsis. If it's a perfectly circular orbit, which is basically impossible, but if it's a perfectly circular orbit, the periapsis and apoapsis are equal. So this thing that I was kind of talking about earlier, the semi-major axis, wow, so many terms that we're introducing, but yeah, so the semi-major axis is the average of the apoapsis and the periapsis. So it kind of gives you an idea of roughly on average how far this body is from this other body. So I don't know. I mean, we were just mentioning Kepler's law, so I thought that was important.
Yeah. A very fun fact, really quickly.
Let's hear it.
There is no equation to calculate the circumference of an ellipse. It doesn't exist.
That is true.
There are ways to approximate it. I know Ramanujan has an equation that is very good at approximating the circumference, but there's no formula. You can't just plug in numbers
That's
and
tough.
get an exact answer.
That's tough.
So
That's
fun
tough.
fact.
That's really tough.
So yeah,
Sad.
the second
Yeah.
law.
Okay. You want to take third, or do I? Or I'll take
you
second.
can go
You
ahead.
take third.
You can go ahead.
I'll take
yeah.
second. I'll take second because
Sure.
why not? So Kepler's second law, right? That states that okay, I didn't think about this before saying it, but an orbit sweeps out equal areas in equal time intervals. Let me explain that. So, wow, I'm actually thinking this would be it would help so much with a visualizer, or like to kind of show what I'm talking about.
I think to put it simply,
How would you? Yeah,
if
I can't think
if
of
we
a way
had to explain it, this is much easier if you were to just watch this on YouTube.
Okay,
but
yeah, it really
Because
would be.
when a planet or a body or whatever is further away from the object, it's moving slower. But as it gets attracted by the force of gravity,
moving
it starts
faster.
accelerating and moves faster. And so in equal periods of time, it's gonna sweep out like a wider triangle when it's closer to the sun, rather
Or
than when
technically
it's
wider
further
arc,
away.
because it's kind of like a part
Yeah,
of an ellipse.
that's right.
So,
It's gonna have a longer arc
yeah.
when it's further away. And so it just turns out that when you look at a set amount of time, the area that it sweeps out, so you calculate like this triangular shape with the arc of the orbit and then the distance to the sun,
The
you
center,
calculate that area is going to be constant for no matter where you are on the orbit. So I don't know, to be honest, I don't know how he figured that out.
That is a pretty interesting thing to figure out when you don't really have anything to
It can be derived
perfectly
though
observe.
when you just take into consideration like the exchange of energy, like from potential to kinetic, and like you of course you have like the position of the sun and then the distance to the sun, and then you can calculate that exchange of energy, and from there when you restrict the time interval, you can derive that the area is equal all over. But you know, you kind of have to have that idea in the first place. You know, I don't think you just stumble upon that idea, which is pretty interesting.
I don't even know how he began to think of that though. Like,
Yeah, and it's crazy how it's true
Like-
though. It's absolutely true.
no, I mean it makes perfect sense though. It makes absolute perfect sense because the farther you are away from a planet, you know, the slower you're traveling, and if you're very very close, you're going faster.
The last great law, and this law is actually as impressive as the last two.
Oh yeah, for sure.
Essentially, it relates the period of the orbit to the distance from, or to the focus in this case. Let's just talk about the Earth and the Sun, just to make it easier. So the distance, and as I said earlier, because the orbit of the Earth is nearly circular, you can kind of approximate that distance by using the semi-major axis, because it's actually the average distance during the entire orbit. And this goes for like even very eccentric orbits. And eccentricity is just kind of like how like
Stretched.
how
quote.
stretched you
Stretched is,
you
I
bring
think, a
out
nice
the
way to
ellipse.
explain that. Yeah.
And so the relationship is that the period squared, and this is in years, and the units matter in this case. You can't just use any
sure.
unit. But the period squared is proportional to the semi-major axis cubed, right? And the semi-major axis has to be calculated in astronomical units. Damn, I can't talk.
Yeah, so
But,
glitched out there.
If you don't know what an astronomical unit is, it is simply the distance from the Earth to the Sun,
Average.
the semi-major
Average
axis.
Yes, exactly.
And if I remember, it's like 100,
Oh, I don't know the number. Do not ask me.
150 million kilometers, 250 million kilometers, something like that.
No idea. But what I do know is the distance is also 8.5 light minutes.
Yeah, of course.
I think this is a common fact that I think some physicists like to, say, or like physics people like to say, hey, I know this cool fact. Because like if the sun died today, blew up today, it would still take 8.5 minutes for us to know. So that's
right.
It's a cool fact
And
to talk about.
something amazing about the law of harmonies is that he was able, like once he came up with this law, he was able to like compare it to the data that they had based on just observing the positions of planets. And it came out to be, very beautiful in the end, because when something is proportional to something else, the ratio of those two is going to be just some number. Mm-hmm. And so he took that ratio for every planet, and it turns out to be like a constant number for every single pair of planet sun. And so that just confirmed his law, and that must have been so cool,